My dear students, Assalamu alaikum. This is the 13th lecture of CS 317 Operating Systems. This video covers the topic of concurrency. We use chapter number 5 of the William Stallings book. In the last lecture, we looked in detail at all the ways processes interact. We discussed examples of deadlock, starvation, and data coherence. We realized the requirements of mutual exclusion. We delved into the hardware approach to implement mutual exclusion. Let us continue our discussion on hardware support for mutual exclusion. How do you satisfy the requirements of mutual exclusion? Well, there are several ways in which these requirements can be met. One approach is to leave the responsibility with the processes that wish to execute concurrently. Processes, whether they are system programs or application programs, would be required to coordinate with each other to enforce mutual exclusion with no support from the programming language or the operating system. We can refer to this as the software approach. This approach is prone to high processing overhead and bugs, so it is not used anymore. A second approach involves the use of special purpose machine instructions. We can refer to this as the hardware approach. These have the advantage of reducing overhead, but nevertheless will be shown to be unattractive as general purpose solution. A third approach is to provide some level of support within the operating system or a programming language. We will examine the last two approaches in this chapter. Two machine instructions deserve a mention here. One is called the compare and swap instruction, and the other is called the exchange instruction. The compare and swap instruction, also known as the compare and exchange instruction. This instruction takes three arguments: a memory location shown here by pointer word. This means that we are passing the address of the location to the instruction. An integer called testval and another integer called newval. And it has a return type which is also integer. It checks a memory location pointer word against a test value testval. If the memory location's current value is testval, it is replaced with newval, otherwise it is left unchanged. The old memory value is always returned. Thus, the memory location has been updated if the returned value is the same as the test value, testval. This atomic instruction therefore has two parts: a compare, which is made between a memory value, pointer word, and a test value, testval, and it is shown here in the red box. If the values are same, a swap occurs in which we assign newval to pointer word, shown here in the orange box. The entire compare and swap function is carried out atomically, that is, it cannot be interrupted. Let us look at the implementation of mutual exclusion using compare and swap. As we move through this code, I am going to give you some awareness of C syntax. In the first line, you see slash asterisk. This is how you put comments in C. Slash asterisk program mutual exclusion asterisk slash means this is a comment. We will declare a constant global integer n. Constant means it has a fixed value. Global means it can be seen by the main program and all the other processes. N will be determining the number of processes that will be created to run in parallel. Bold is a global variable. There is always a main function in C code from which execution starts. In the main function, before the creation of processes, bold is initialized to 0. The par begin construct creates n processes that will execute code P and admits them to the ready queue all at the same time. The construct par begin means the following: suspend the execution of the main program, initiate concurrent execution of n procedures that would execute code P, and when all of the parallel processes have terminated, resume the main program. Each created process will execute the code that is written in the function of P. Let us see what happens in function P. There is an outer while, which means the process will never terminate, it will keep looping forever. The body of the outer while extends from the curly bracket after it to the second last curly bracket, the one after remainder. The last curly bracket in the red box marks end of body for the function P. In C, each statement ends at a semicolon. Look at the second or inner while loop. Where does it end? After do nothing. Right. Do nothing itself is just a comment. It is here to show you that if the condition of the while is true, you slip into the body of the while loop, but there is nothing to do there. So you go back to the checking condition, which is true. So you slip into the body, which is empty. So you go back to checking the condition, which is true, and so on. Get the picture? Remember that the compare and swap compares the first argument with the second. And if the result is true, it swaps the value of the first argument with the third. Then it returns the old value of the first argument. A process trying to get into critical section fetches the value of bold and compares it with 0. If the comparison is successful, bold is updated to 1. Value returned is 0, which is the old value of bold. So the while condition becomes false and the process proceeds to the next line of code instead of slipping into the while's body. In other words, the process enters critical section. Again, critical section is a comment which can be replaced with code that would be manipulating shared modifiable data. If bold was previously 1, the compare returns false. No swap occurs. Value returned is 1, which is the old value of bold. And the executing process slips into the body of the while loop, in which it keeps executing compare and swap repeatedly. Every time it compares, the result is false, the return value is 1, and it slips back into the while. A process can escape the second while if someone changes the value of bold to 0. Then the compare will be true. Bold will be swapped by 1. The return value will be 0 and the while condition will become false. When a process leaves critical section, it resets bold back to 0. After this, the first process who compares the value of bold with 0 gets to come out of the nasty while. Now I will do an example run of the code that you just saw, and I am going to elaborate it in a different way. Consider three processes P1, P2 and P3 trying to enter their critical sections and using the compare and swap instruction to implement mutual exclusion. If the code is correct, mutual exclusion will be enforced no matter what assumptions we make regarding the relative speeds of these processes. Some points are worth remembering. Compare and swap compares bolt with 0. If the comparison is true, it swaps bolt with 1. Compare and swap always returns the old value of bolt. For the purpose of demonstration, we assume P3 to be the fastest. The main program starts and sets bolt to 0. We assume the constant integer n has been initialized to 3. The par begin construct begins 3 processes in parallel. Being the fastest, P3 hits the second while loop first and compares bolt with 0. The comparison is true, so bolt is set to 1. Compare and swap returns the old value of bolt, which is 0. The while condition becomes false. P3 does not move into the second while's body. Instead, it lands into its critical section. P1 is the next to hit the second while and compare bolt with 0. The comparison is false. Bolt remains as it is. Compare and swap returns the old value of bolt, which is 1. The while condition becomes true. P1 is caught in the second while's body, where it repeatedly executes the compare and swap. Every time the comparison is false, bolt remains as it is, the return value matches 1, and P1 remains caught in the loop. P2 is the next to hit the second while and compare bolt with 0. The comparison is false. Bolt remains as it is. Compare and swap returns the old value of bolt, which is 1. The while condition becomes true. P2 is caught in the second while's body, where it repeatedly executes the compare and swap. Every time the comparison is false, bolt remains as it is, the return value matches 1, and P2 remains caught in the loop. P3 has had enough time in critical section now. When it moves out of the critical section, it sets bolt to 0. Both P1 and P2 have been constantly comparing the value of bolt with 0 all this time. The first one among these to realize that the value of bolt has changed will escape the while. Let us assume that between P1 and P2, P2 checks bolt first after P3 has changed it. P2 compares bolt with 0. The comparison is true, so bolt is set to 1. Compare and swap returns the old value of bolt, which is 0. The while condition becomes false. P2 does not move into the second while's body. Instead, it lands into its critical section. Do you notice the first while? This will make P3 loop in its code again. P3 hits the second while and compares bolt with 0. The comparison is false. Bolt remains as it is. Compare and swap returns the old value of bolt, which is 1. The while condition becomes true. P3 is caught in the second while's body, where it repeatedly executes the compare and swap. Every time the comparison is false, bolt remains as it is, the return value matches 1, and P3 remains caught in the loop. P2 has had enough time in critical section now. When it moves out of the critical section, it sets bolt to 0. Both P1 and P3 have been constantly comparing the value of bolt with 0 all this time. The first one among them to realize that the value of bolt has changed will escape the while. Let us assume that between P1 and P3, P1 checks bolt first after P2 has changed it. P1 compares bolt with 0. The comparison is true, so bolt is set to 1. Compare and swap returns the old value of bolt, which is 0. The while condition becomes false. P1 does not move into the second while's body. Instead, it lands into its critical section. The first while makes P2 loop in its code again. P2 hits the second while and compares bolt with 0. The comparison is false. Bolt remains as it is. Compare and swap returns the old value of bolt, which is 1. The while condition becomes true. P2 is caught in the second while's body, where it repeatedly executes the compare and swap. Every time the comparison is false, bolt remains as it is, the return value matches 1, and P3 remains caught in the loop. This is the table that I make for my students on the whiteboard. This is called a parallel trace. This parallel trace is for the same example that I just enumerated for you. On the top left, I have the code of each of the processes. I have removed the global variable declarations and the main program due to lack of space. When we begin, bold is 0. For a parallel trace, we normally make a set of assumptions. Our first assumption is that P3 is the fastest of all processes. So it does a compare and swaps bold to 1 and enters critical section. After P3, we assume P1 does a compare. No swap occurs as bolt is 1 and P1 is caught in the second while. When a process is repeatedly executing an instruction which keeps it caught in the same loop, we call this busy waiting. So P1 is busy waiting. We assume P2 does a compare last. No swap occurs as bolt is 1 and P2 is caught in the second while, so P2 is busy waiting. P3 leaves the critical section, sets bolt to 0. We assume P2 compares bolt first and swaps bolt to 1 and enters critical section. We assume P3 starts the outer while loop again. P3 does a compare, no swap occurs as bolt is 1 and P3 is caught in the second while. So P3 is busy waiting. P2 leaves the critical section, sets bolt to 0. We assume P1 compares bolt first and swaps bolt to 1 and enters critical section. We assume P2 starts the outer while loop again. P2 does a compare. No swap occurs as bolt is 1 and P2 is caught in the second while. So P2 is busy waiting. When we leave them, P1 is in its critical section and P2 and P3 are busy waiting, checking the value of bolt again and again. The term busy waiting or spin waiting refers to a technique in which a process can do nothing until it gets permission to enter its critical section, but continues to execute an instruction or set of instructions that test the appropriate variable to gain entrance. The exchange is the second machine instruction that we use for implementation of mutual exclusion. We provide addresses of two locations as arguments, register and memory. The instruction does not return any value, hence the word void before exchange. An important point to note is the instruction is atomic, that is, it cannot be interrupted. It either completely executes or does not execute at all. The instruction exchanges the contents of a register with that of a memory location. Both the Intel IA32 architecture or Pentium and the IA64 architecture or Itanium contain an XCHG instruction. Now I will examine the mutual exclusion code using exchange instruction. I am not using a snapshot of code from the book because there is a coding error in figure 5.2b. Please do not refer to it. We will declare a constant global integer n. Constant means it has a fixed value. Global means it can be seen by the main program and all the other processes. N will determine the number of processes that will be created to run in parallel. Bolt is a global variable. There is always a main function in C code from which execution starts. In the main function, before the creation of processes, bolt is initialized to 0. The par begin construct creates n processes that will execute code P and admits them to the ready queue all at the same time. Let us see what happens in function P. Each process has a local variable key I which is initialized to 1. There is an outer while, which means the process will never terminate. It will keep looping forever. In C, we have something known as a do-while loop. You can see a do-while loop here. It is similar to a while loop. However, the condition is checked at the end of execution of the body of the loop. So this means the body executes at least once, even if the condition is false. A process trying to get into critical section fetches the value of bolt and exchanges the value of bolt with key I. After the exchange, key I is compared to 0. If key I is equal to 0, the condition of the while becomes false and the process moves into its critical section. Critical section is a comment which can be replaced with code that would be manipulating shared modifiable data. If key I is not equal to 0, the condition is found true and the process loops back to exchange key I with bolt. Again key I is compared with 0 and if unequal, the process loops back to exchange the two values. So if key I is not equal to 0, the process is caught in the loop, doing the same exchange again and again. This is busy waiting. When a process leaves critical section, it sets bolt back to 0 and key I to 1. The process which makes the exchange right after the departing process proceeds to critical section. If some other process changes bolt to 0, the process caught in the loop will get its key I equal to 0 the next time it exchanges key I with bolt. On the top left, I have the code of each of the processes. I have removed the global variable declarations and the main program due to lack of space. So again, we try to draw a parallel trace, this time with the exchange instruction. When we begin, bolt is 0. Our first assumption is that P1 is the fastest of all processes. So it exchanges its key I with bolt. Bolt goes to 1. Its key I becomes 0. And P1 enters critical section. After P1, we assume P2 exchanges its key I with bolt. Both variables are 1 and P2 is caught in the do while. So P2 is busy waiting. We assume P3 exchanges its key I with bolt last. Both variables are 1 and P3 is caught in the do while. So P3 is busy waiting. P1 leaves the critical section, sets bolt to 0, key I to 1. We assume P3 exchanges its key I with bolt first. Bolt goes to 1, P3's key I becomes 0, and P3 enters critical section. We assume
P1 starts the outer while loop again. P1 exchanges its key I with bolt. Both variables are 1 and P1 is caught in the do while. So P1 is busy waiting. P3 leaves the critical section, sets bolt to 0, key I to 1. We assume P2 exchanges its key I with bolt first. Bolt goes to 1, P2's key I becomes 0, and P2 enters critical section. We assume P3 starts the outer while loop again. P3 exchanges its key I with bolt. Both variables are 1 and P3 is caught in the do while. So P3 is busy waiting. When we leave them, P2 is in critical section and P3 and P1 are busy waiting, exchanging their respective key I's with bolt again and again. The use of a special machine instruction to enforce mutual exclusion has a number of advantages. It is applicable to any number of processes on either a single processor or multiple processors sharing main memory. It is simple and therefore easy to verify. It can be used to support multiple critical sections. Each critical section can be defined by its own variable.
But there are disadvantages to machine instruction approach. The first is busy waiting is employed. When a process is waiting for access to a critical section, it continues to consume processor time. The second is starvation is possible. When a process leaves critical section and more than one processes are waiting, the selection of a waiting process is arbitrary. Thus, some process could indefinitely be denied access. Arbitrary means no selection criterion. This is a totally unfair policy. Somebody might argue how. Let me give you an example. I give out bonus marks in every online session, but I do so arbitrarily. This means I require no reason to select someone. This also means that I require no reason to ignore someone. So I pick a student Ali and I award him bonus marks in the first session. Then I award him bonus marks in the second session. Then I do the same in the third session, and so on. Now, if the class is angry at me, they cannot hold me accountable because when they ask how I select Ali, I simply smile and say arbitrarily. Why is the class angry with me? Because by picking Ali every time, I am making all the rest of the students starve. The third disadvantage is deadlock is possible with machine instruction approach. Consider this scenario. Process P1 executes the special instruction and enters its critical section. P1 is then interrupted to give the processor to P2, which has a higher priority. If P2 now attempts to use the same resource as P1, it will be denied access because of the mutual exclusion mechanism. Thus, it will go into a busy waiting loop. However, P1 will never be resumed because it is of lower priority than another ready process, P2. P1 waits for P2 to run and finish off. P2 waits for P1 to leave critical section. Before I leave this topic, I want to leave you with some homework. Draw up parallel execution traces using the following conditions. Use compare and swap with 4 processes, assuming the order of entry into critical section to be P3, P1, P2, P4. The second task is use exchange with 2 processes, assuming the order of entry into critical section to be P2, P1, P2 and then P1. There are three mechanisms that are used to provide support for concurrency and are implemented in either the operating system or the programming language. These are semaphores, monitors, and messages. Now we begin our discussion on semaphores. The fundamental principle is this: two or more processes can cooperate by means of simple signals, such that a process can be forced to stop at a specified place until it has received a specific signal. Any complex coordination requirement can be satisfied by the appropriate structure of signals. So, how are these signals transmitted and received? To transmit a signal via semaphore S, a process executes the primitive sim signal S. To receive a signal via semaphore S, a process executes the primitive sim wait S. If the corresponding signal has not yet been transmitted, the process is suspended until the transmission takes place.
The semaphore is a variable that has an integer value upon which only three operations are defined. A semaphore may be initialized to a non-negative integer value. So you can initialize the semaphore to a value greater than or equal to 0. The sim wait operation decrements the semaphore value. If the value becomes negative, then the process executing the sim wait is blocked. Otherwise, the process continues execution. The current value of S is 1. Suppose process A does a sim wait. The value decrements. As S is not negative, A continues execution. Now assume process B does a sim wait. The value decrements. The value of S becomes negative, so B is placed in the queue associated with semaphore S. We say B is blocked on S. Again assume process C does a sim wait. The value decrements. The value of S becomes negative, so C is placed in the queue associated with semaphore S, and we say C is blocked on S. The sim signal operation increments the semaphore value. If the resulting value is less than or equal to 0, then a process blocked by a sim wait operation, if any, is unblocked. Suppose any process other than B and C does a sim signal. The value increments. B is unblocked and resumes execution. Suppose any process other than C does a sim signal. The value increments. C is unblocked and resumes execution. Other than these three operations, there is no way to inspect or manipulate semaphores. On this slide, I give you the semaphore primitives. As I told you before, primitives are functions that execute atomically, that is, they are not interrupted during execution. The semaphore is implemented as a structure. Structure is a user-defined data type in C language which allows us to combine data of different types together. Structure helps to construct a complex data type which is more meaningful. In the structure of semaphore, there is an integer variable count that will keep the value of the semaphore. The programmer must have defined a data type by the name of queueType earlier, which would implement a queue. An instance of this queue is instantiated in our structure to complete semaphore definition. When a process calls simWait, the count variable of the corresponding semaphore is decremented. Then we check if count is less than 0. If this is not the case, nothing more happens. If this is in fact true, we place the calling process in the queue of the semaphore, blocking it. When a process calls sim_signal, the count variable of the corresponding semaphore is incremented. Then we check if count is less than or equal to 0. If this is not the case, nothing more happens. If this is in fact true, we remove a process from the queue of the semaphore and place it in the ready queue. P and V operations. The first major advance in dealing with the problems of concurrent processes came in 1965 with Dijkstra's treaty, in which he proposed the concept of semaphores. In Dijkstra's original paper and in much of the literature, the letter P is used for simwait, stands for proberen in Dutch, which means test. The letter V is used for sim_signal, stands for verhogen, which means increment in Dutch. Let us elaborate on the significance of the value of a semaphore. To begin, the semaphore has a 0 or positive value. If the value is positive, that value equals the number of processes that can issue a wait and immediately continue to execute. If the value is 0, either by initialization or because a number of processes equal to the initial semaphore value have issued a wait, the next process to issue a wait is blocked and the semaphore value goes negative. Each subsequent wait drives the semaphore value further into minus territory. The negative value equals the number of processes waiting to be unblocked. Each signal unblocks one of the waiting processes when the semaphore value is negative. There are three major consequences of semaphore definition. In general, there is no way to know before a process decrements a semaphore whether it will block or not. This is because you cannot access and read the value of the semaphore at any time. After a process increments a semaphore and another process gets woken up, both processes continue running concurrently. There is no way to know which process will continue immediately on a uniprocessor system. It can be the process who issued a signal and incremented the semaphore. It can be the process who got out of the semaphore queue, and it can be another process from the ready queue. When you signal a semaphore, you don't necessarily know whether another process is waiting. So the number of unblocked processes may be 0 or 1. This is because you cannot access and scan the queue of the semaphore at any time.
We looked in detail at the compare and swap instruction. We learned how to trace the execution of parallel or concurrent processes. We looked in detail at the exchange instruction. We conducted an analysis of the machine instruction approach to mutual exclusion.
Finally, we learned about semaphores. At the end of this lecture, I ask you to read the book and do the homework that I assigned. Make parallel traces for both machine instructions using the assumptions that I have given you, and if you need to make more assumptions, make them and write them alongside the parallel trace so that when you look at your parallel trace again, you can understand why you did a certain thing or you wrote a certain point. Write your questions on a piece of paper and keep it in front of you during the online session. If you have suggestions relevant to content or quality of this lecture, email them to me. Do tell me if you like the animation that I showed you in this slide and if you understood it. Take care of yourself. We'll meet again. Allah Hafiz.